Hello and welcome back to Calculus 1. Yes. Fundamental theorem of calculus. Very, very important. So this theorem has two parts, and the part one you already know. Part one of fundamental theorem of calculus is you calculating the definite integral. So the part one is that the integral a to b f of x dx is any antiderivative computed from a to b, which is f of b minus f of a. This computes the area, and you have to be careful, whether the function dips below x-axis or not, and if it does, you have to, so this calculates net area. If you want to calculate the area that you get to color, if the function dips below x-axis, if it has negative y's, you have to use absolute values. You have to break it apart. So fundamental theorem of calculus, the first part one is the definite integral calculation. Part two. The derivative of the integral of a to x of f of t dt is equal to f of x. Now this is a theoretical result which you hopefully see that says, what does it say? Can anyone tell me what is this equation trying to say?
I'm not sure, but I think that if it wasn't for the x-ray, it would have canceled, right? Because the integral was antiderivative.
Yeah, exactly that. So,
but what's more confusing is that even with that, how does that compute to a single y value? If the derivative itself is shown as a function, how is it a y value? Even if it is from
well, I'm going to do a proof for this. So it will be clear. Your question will be clear, but my question is, so this, what did you say? So what is this saying? This formula is saying that integral and derivative cancel each other out. They're opposites of each other. They're opposite operators. So you know how addition and subtraction are opposite operations, multiplication and division, right? Or exponents and logs are opposites. They're inverse operations. These guys are inverse operators. And we can prove this calculation easily, because when you start with a definite integral, you copy the derivative, and what you get is that the integral of f of t is capital F of t from a to x, which further tells us that we are now using the part one where we compute. So derivative of f of x minus f of a. Now you know that this part over here is just a number, right? F of a. So when you take the derivative of capital F is the lowercase f, and then minus 0. So it's just f of x. No, x is a variable.
Well, it's normally a variable, but the fact that it's there on the integral means that it's a value.
No, you can put the variables as well. But the trick is that, as you can see, it is the variable for the derivatives. It is a value for, it is a parameter for the integral, but for the derivative, it's a variable. So the integral operates on t. Oh, I put dx over here. Wow, terrible. So the integral operates on t, and then when we plug in x, we get the function of x, and then when we differentiate in respect to x, x is a variable. So now I want to do the example for this. Integral 3 to x of x cubed dx. Oh, sorry, t cubed dt. So what do? We write d dx, and now the integral is t to the 4 over 4 computed from 3 to x. d dx equals 2, and now I have x to the 4 divided by 4 minus 3 to the 4 divided by 4. So when you take the derivative, now this is a number, so it's going to go to 0. So when I take the derivative of x to the 4 is 4x cubed divided by 4, which I'm copying, minus 0, and there it is, x cubed.
I'm not sure if it always works out like that, but does that mean that f of t is equal to f of x with the xt substitution?
Yes. That's exactly what it means. So this and this will always be the same because they're opposite operators. And the opposite, you know about opposite operations. You know that, let's say, 3 plus 5 is equal to 8, and then 8 minus 5 is equal to 3. You know that. You also know that if you're using function, let's say f of x equals x plus 2, and you're using its inverse, which in this case is x minus 2, you can plug in, let's say, 10 over there. You will get 12. When you plug 12 over here, you get back 10, right? So the thing is that when you do composition of these two inverses, so if you do function composed with the inverse, you just get x back, right? You get the original x back. So the idea over here is to show that integration and derivative are opposite operators, and you can change the function with the derivative, then you can integrate it to bring it back, or you can integrate the function and then do the derivative to go back, which we learn through velocity and acceleration and position function. We learned that if you have a position function, you differentiate in respect to time to get the velocity function. You differentiate in respect to time to get the acceleration function. But you can also integrate in terms of time from acceleration to go back into velocity, and you can integrate back again in respect to time velocity to get the position. So you can do all of those things back and forth because, again, operators are opposite of each other, derivative and integral. Can anyone tell me why are they opposite of each other? Why are they opposite?
Create a function, or rather an operator, to do the opposite of derivative. You call an integral, thus an integral is the opposite.
Well, that's true. They're both, but let's consider their formulas, right? both integral and derivative are defined through the limit. So do you see why are they? Can you tell me what was the formula for the derivative? Anyone remembers the definition? Limit?
Limit as it goes to 0 at x plus a minus f back everything over a.
Perfect. Who can tell me what's the formula for the integral? H was f minus b minus a. What was the formula for integral? We did it yesterday. Come on. You recall one that was done a month ago. How about the one that was done yesterday? Limit.
Like n equals infinity of sum of I equals 1 below n of integral f of x I delta x.
Good. Got it. It's arrived. Why are these two opposite of each other? What do you see there? Nice. Perfect. You see why they're opposite. Look, the formula on top, they both have limit, right? One limit goes to 0, the other one goes to infinity, right? That's opposite. But look at this. This formula here is fueled by subtraction and division, right? And the formula on the bottom has addition and multiplication. Do you see that? They're completely opposite of each other. Obviously, they both operate on a difference, and you have difference in both of them. But the key point is that the derivative is difference quotient, and this is sum of the product. So you can also see through their definition that they are completely opposite of each other. So now, if I ask, what is the integral? I don't want to use 3 again. Let's use a different number, 16. X of secant t dt. What is your answer? Done. That's all it is. Right? And believe it or not, the lecture is done. Yeah. Guys, this is extremely important because your application depends on it. To know which one to apply when you're facing engineering problem, are you going to use the derivative or are you going to use integral? No one cares if you can compute them because machine is going to do that for you. The question is, what do you tell the machine to do for you? That's what you get paid for. So if it is a change, a rate of change of some kind, it's a derivative. If it's accumulation of some kind, it is the integral. So you should do as much application as you can so you can recognize these things for your future classes. All right, so we are going to take the break and then we're going to go through those 3 formulas in 5.4.